So this is the review session for Chapter 5 of Calculus, AP Calculus BC. And this is basically an overview of derivative tools and applications. So we start off with applications, mainly to graphs of functions. First of all, we talk a bit more about position, velocity, and acceleration. And we formally say that the relationship between them is position, velocity, acceleration, where velocity is the derivative of position and acceleration is the derivative of velocity. And if we go the other way around, position is the antiderivative of velocity and velocity is the antiderivative of acceleration. And there are example problems as well, saying if the equation for position is negative 16t squared plus 40t plus 4, what does this basically mean? So the general meaning of it is that the negative 16 represents 1/2 of the acceleration, because to take the derivative of it, we get negative 32t plus, and then this just becomes 40, and the derivative of that is just negative 32. So the acceleration is just negative 32. The velocity is negative 32t plus 40. So this is the initial velocity. This is the acceleration. And finally, for the position, this is 1/2 of the acceleration. This is the initial velocity, and this is the initial position. So those are some things you should keep in mind. Whenever you have something being thrown in the air or kicked in the air, anything like that, the acceleration will always be negative 32, because in feet per second squared, that is the acceleration due to gravity. If it was in meters per second squared, it would be negative 9.8. So depending on the units, it'll either be negative 32 or negative 9.8. After that, they talked about an application of derivatives to graphs. So first of all, what are extreme values? Extreme values are basically maximums or minimums, and there are two types. There's local and there's global. Local is also called relative, global is also called absolute. You can use them interchangeably, basically, because they mean the same thing. Now, if you have a graph like this, as an example, what is the local maximums and local minimums? Well, this is definitely a maximum, because on the other sides of it, it is less than the actual value on both sides. So it is a local maximum. This is a local minimum, same reason, except the other points are above it on both sides. There's also local maximum, same reason, and local minimum. So we have 4 local extreme values. What about global? Global is basically the absolute, or the only maximum and the only minimum. So that would be this one right here and this one down here, because that is the highest maximum and this is the lowest minimum. So there can only be up to 2 global extreme values of a function. There can even be 1 if you have something like a parabola, and 0 if you have something like a line. But there is something called the extreme value theorem. And this extreme value theorem basically states, if you have a closed interval, AB, closed is important, then there will be a global minimum and there will be a global maximum in that interval. You may argue, well, what about the line? There is no global minimum nor global maximum on the line. That's because it's not a closed interval. It's just going to infinity on both ends. If we restrict it to, let's say, -2 to +2, then yes, there will be a global minimum, this one, and a global maximum, that one. The thing about extreme values is that they can be the endpoints. That's why it's so important that it has to be a closed interval. If it was open, it would be something like this, and you wouldn't have a global minimum or maximum. You just say that if it was closed, it would be this point, and this point would be the maximum, this point would be the minimum, but it's not closed, so there's none. That's why it's closed. And any function that is continuous over the closed interval AB has a global minimum and a global maximum. So whenever a problem asks you to find what is the global maximum, you have to consider everywhere where you have a horizontal tangent, basically a critical point, and you also have to consider the endpoints because they could be global minimums and global maximums. Another example, you have a parabola like this. The maximum, the global maximum is this, while the global minimum is actually not an endpoint. So it doesn't have to be the endpoints. It doesn't have to be the critical points. It could be either. That's the extreme value theorem. Now, what about critical points? How do we find those? So we talked about endpoints and how you have to test those. What about critical points themselves? How do we find those? Well, critical points are when f prime of x is either equal to 0 or does not exist. So you basically use this fact to find where the critical points are. So if you have a function like 3x cubed, you find the derivative of it, which when you bring down the 3, you get 9x minus 1, so 3 minus 1 is 2. 9x squared, you find out when that's equal to 0. This is a pretty bad example, actually, because even the second derivative, which is 18x, is also equal to 0, so it's actually not like a critical point here. But if it was another function, then yes, you would use the first derivative to find the critical point. And you would use the second derivative to find the points of inflection. This was introduced in chapter 3, actually. But going more in detail, how do you determine if it's a maximum or minimum? Specifically, because all you know is that it's a critical point. There are two ways. The first one is called the first derivative test. And as expected, it uses the first derivative. It says it's a maximum if obviously f prime of x equals 0 does not exist, and f prime of x minus h, where h is some small amount, is greater than 0, f prime of x plus h is less than 0. What it's basically saying is if you have something like this, at the point x, it is 0, the slope, but as you move slowly away in the positive direction, so that'll be the second case right here, you want it to have slope less than 0. In this case, it's greater than 0, which means it's not a maximum. Instead, it's a minimum. Minimum, basically inverse of these rules. To the right should be positive, to the left should be negative. That's what you get if it's a minimum. If it's a maximum, like something like this, again, at the point itself, it's equal to 0. A bit to the right, it's negative, and a bit to the left, it's positive. So that follows this, which means based on the first derivative test, it is a maximum. The first one is a minimum because it basically does not follow the maximum rules, therefore it's a minimum. It's basically the opposite of this. The second derivative test is basically, again, you look if f prime of x equals 0, and then it's a maximum if f double prime of x, the second derivative, is less than 0. So it's basically saying, is it concave down? And concave down and a horizontal tangent basically means it's a maximum. Yeah, a minimum is if it's concave up and equal to 0 does not exist. So these are the two cases, and the second derivative test tells you based on concavity. So the second derivative test is usually easier because you only have to find one thing rather than two different values. But depending on if the second derivative is a very complex function, you might want to stick with the first derivative. So let's do an example. If you know that for a certain graph, f prime of 2 is equal to 0, f prime of 1 is equal to -1, and f prime of 3 is equal to 1, is it a maximum or a minimum? Well, we have a horizontal tangent here, which means it's a critical point. When it's less than, or when it's to the left, it's a negative slope. And when it's to the right, it's a positive slope, which means that it should be a minimum. So using the first derivative test, based on just these three values, we found out that it's a minimum at the point x equals 2. We can do even better with just two values. Let's say we know that f prime of 2 is equal to 0, and f double prime of 2 is equal to -4. Just two values, we can determine if it's a minimum or maximum. So we know it's a horizontal tangent here. And this is a negative, the second derivative is negative, which means it's concave down. Therefore, it's a maximum. Concave down and a critical point means maximum. So these are basically the first and second derivative tests in action for an example problem. Moving on, there's a bunch of rules that follow. There's 3 rules and then a few derivatives you should memorize. So that was the derivative applications. Now we're moving on to the derivative tools. The first one is the product rule. Basically, if you have f of x times g of x and you want to find the derivative of that, you do f prime of x times g of x plus f of x times g prime of x. It's always best to introduce these tools with an example. So let's say it's x times sine x. What's the derivative of this? Without the product rule, we can't really do much. So applying it, this is f of x, this is g of x. F prime, well, that's derivative of x, which is just 1. Just g of x itself, so it's sine x. And then just f of x, so it's just x. And then g prime of x. What's the derivative of sine? It's cosine. So your answer will be sine x plus x cosine x. That's the derivative of x sine x. And you can verify that with the calculator or anything, but this is an example of how you use the product rule. There's a similar one called the quotient rule, and the textbook actually introduces the chain rule before the quotient rule, but I prefer to do the quotient rule first. I think the reason why it introduces the chain rule first is because in order to prove the quotient rule, you need to use the product rule and the chain rule, which is why it does that. But since this is just a recap of the chapter, I'm not really going to prove these rules. I'm just going to show you the formulas and examples of them. So how do you use the quotient rule? If you have f of x over g of x, how do you find the derivative? Well, it's equal to f prime of x times g of x, similar to the first one, but then it's minus f of x times g prime of x. So now in this case, order matters. For that one, you don't really have to memorize much because order doesn't matter. You can flip it around and get the same result. But here, order matters. So remember, it's always f prime of x at the start. Over g of x squared. So whatever function it is squared. Let's do an example. Let's say the function is x cubed over 2x plus 1. You could technically product rule is an option, but quotient rule is faster if you know the formula. Of course, if you forget the formula, then just product rule it. Product rule and chain rule, so you're gonna have to memorize those two. But quotient rule makes things a bit easier because it's just one formula you plug in instead of two. So let's do this. F prime of x. So what's the derivative of x cubed? It's 3x squared. So that times g of x just by itself is 2x plus 1 minus f of x is x cubed. G prime of x is derivative of that, which is just 2 over this squared. So it's 2x plus 1 squared. Now we can do a bit of simplifying here, and we get in the denominator, first of all, we use the product, the square of binomial. We get 4x squared plus 4x plus 1. And then in the numerator, we get 3x squared times 2x, which is 6x cubed. And then we see a x cubed minus 2 times 2 here, which is 2x cubed, and we subtract that, which means this is actually 4x cubed plus 3x squared times 1 is just 3x squared. And then we already dealt with the x cubed times 2, which means this is our final answer. So that's the product rule and the quotient rule, both the formula and an example. Final rule is chain rule. Chain rule is honestly, it's not as easy as the product rule, but it's not as complicated as the quotient rule either. So chain rule basically says if you have a composition of two functions, f of g of x, and it can be something as simple as sine of 2x. 2x is the inner function, sine is the outer function. The derivative of that is just f prime of g of x times g prime of x. So you take the inner function, take the derivative of that, and then multiply it by the derivative of the outer function with respect to the inner function. That's a bunch of words, but an example would make it much easier. So let's say, like I mentioned, sine of 2x. It's a relatively easy problem. You would first take the derivative of 2x, which is 2. And since it's multiplication, the commutative rule says we can switch it around, which is why I'm starting with taking the derivative of the inner. You could do any way you want it, but I just feel like it's easier this way. Now you take the derivative of sine x. So notice we're not taking the derivative of sine 2x because that puts us in an infinite loop, because the derivative of sine 2x is what we're trying to find. Instead, we're trying to find the derivative of sine of u, where u is equal to 2x. That's in the form proof and everything like that. If you're just looking at the formula and you're just good at memorizing stuff, completely fine if you ignore u and everything. But basically, what you're saying is, oh, u is equal to 2x. You're taking the derivative of sine of u with respect to u, which means the derivative of sine is cosine, so it's cosine of u. And u we can replace now with the original function 2x, which means the derivative of sine 2x is 2 cosine 2x. I think another example would be very helpful. Let's say we have 4 cosine x squared. Now, this is a mixture of rules. It's the product rule and the chain rule. So this example really highlights the rules in action. So first we take the derivative of the inner. That's the product rule part. So let's do it. First, actually, let's make it 4x, because if it's just 4 cosine, you don't need the product rule. 4x times cosine x. Derivative of 4x is 4 times cosine x. And then we add just 4x by itself times derivative of cosine x is negative sine x. So we turn this into a negative sign. And we have this. So this is just the derivative of the inner function. Now we take the derivative of the outer function. So that becomes 2 times whatever the inner function is to the power of 1, because we're bringing down the 2 and subtracting 1. So we get the inner function as 4x times cosine x. And then just that. So if you want to simplify it a bit more, which honestly you don't have to do, you can combine this, get 8x times cosine x, and then distribute it out. So you get 32x, because this was 8x cosine x. 8x times 4 is 32x, and then cosine x times cosine x is cosine squared x, minus, again, 4x and 8x makes 32x squared, times cosine x times sine x is just sine x cosine x. And that gives you the derivative of whatever this original function was. So this uses both the product rule and the chain rule. So if you want some practice like this, uh, try to find functions that use multiple rules, maybe even all three if you're up for the challenge. That's definitely going to take more space and be more complicated, but if you want to, go ahead. And then just something brief to mention, the derivatives of the 6 trigonometric functions. It's just a bunch more memorization. You can't really like you can prove it actually. It's possible to prove it using the rules we learned, but if you're good at memorization, you can just memorize it. If not, you can try to derive a proof using the product and quotient rules. All I'm saying is for each trigonometric function, try to write it in terms of sine and cosine, and then use one of the three rules or multiple of the three rules maybe to find the derivative if you want to prove it. So probably the best way to highlight it is using a table. So we have 6 functions. It's sine x, tan x, and secant x. Cosine x, cotangent x, and cosecant x. You might be wondering why I split sine and cosine here and all that. It's because these are the co-functions of these. So basically the derivative has something to do with the cofunction. It's not that prevalent, but it could definitely help with memorization. So the derivative of sine is cosine, we know that. Derivative of cosine is negative sine. We can fill that out. Already we see something. Cosine is negative while sine is positive. And these are just switching the trigonometric function. Maybe it's a coincidence, maybe not. What's the derivative of tan? It's secant squared x. Again, if you want to prove it, feel free to prove it, but I'm just providing you with the formulas that you should memorize. Cotangent x is negative cosecant squared x. Again, we see something. Negative, positive. Cosecant, secant. Again, those are cofunctions. So if you find tangent, you can find the derivative of cotangent by just taking the negative and then replacing every function in that derivative with the cofunction. Let's see if it works for secant. Derivative of secant x is secant x times tan x. Let's see what we get if we try to use our rule or pattern that we identify. We should get negative cosecant x times cotangent x. And voila, yes, that is the derivative of cosecant x. So if you want to memorize it that way, feel free to. If you just memorize 6 trigonometric functions, go ahead. If you want to prove it, or go ahead. You can do anything that works for you. There's one more thing to mention, and that's optimization. And that's a big topic. So I'm going to try to condense it as much as possible to fit in a recap. There's 6 main steps. The first one is to draw a diagram. Second step is to write an equation. Third step, write other important equations. Fourth step is to solve for one variable. And the fifth step is to optimize using derivatives. So this is actually the optimization part. The rest is just algebra. This is the only calculus part of it. And then finally, you just solve the value you want in the question. So again, like I said, best way to learn it is through an example. So let's do an example. You have 40 feet of fencing. You want to make a square fence and a circle fence, and you want to minimize the area. For some reason, you just want to minimize it. Don't question it. It's a word problem. You want to know how much you should leave for the square and how much you should leave for the circle. So let's say you leave x for this. First, draw a diagram. We did that step. Let's define variables. Let's say x is how much you use for the square, which means 40 minus x is how much you use for the circle. So one thing to note is that x is not the side length of the square. It's the perimeter of the square because it's how much we're using for the entire square, not just one side of the square. Similarly, 40 minus x is not the radius. It is the circumference of the circle. Second step is to write an equation. So we know that honestly, in this case, we don't really need the second step because there's only one equation we care about, and that is the total area is equal to the area of the square plus the area of the circle. I guess this is technically writing the equation because there's x and y, which are the two lengths, and you just replace y with 40 minus x. This is a relatively simple problem in that we don't need another equation. There are other problems like surface area and volume. You're given surface area, you need to maximize volume, something like that. So let's convert this into a function. F of x is equal to, so what's the area of the square? We'll first define the side length. We do x over 4 to get the side length of the square. Now we square that because it's a square. So that's the area of the square. Now what about the circle? Well, we know it's pi r squared. What's the radius? Well, we know the circumference is 40 minus x, and that is equal to 2 pi r, which means that the radius is 40 minus x over 2 pi. You just divide both sides by 2 pi and you get that, and you have to square it because it's pi r squared. Now, you would need to find the derivative of this function, which is actually kind of complicated. You could technically use some rules. I don't think you would want to, but if it's a no-calc section, which I doubt, you might want to practice doing derivatives, and you might want to do these problems. You should be able to, theoretically speaking. But for the purpose of this example, I'm not going to show my work on how to calculate the derivative. Instead, I'm just going to write the value for which the derivative is equal to 0. You could calculate the derivative and then solve the algebraic equation by hand, but since we're running out of time, we are forced to just use a calculator in this. If I have time at the end, I'll show you how to find the derivative. So we get x is equal to 22.404. Again, I did not show you what the derivative was even. I just solved it for equal to 0. That's missing a big step, which is the calculus, and I'll definitely show it if I have time. But for now, I just want to show you how to do the rest of the algebra, because that's the hardest part. The calculus is what we've been doing for the past few months. The algebra is what trips up most people. So now that you're given this, is that the final answer? It's close. This time it's asking for both the square and this circle. So the perimeter of the square is this. Feet, don't forget feet, because that's the unit. And what's the circumference of the circle? Well, we just do 40 minus the answer, and we get 17.596 feet. So that's how much you use for the square. That's how much you use for the circle. A slightly more complicated problem would be, what is the total area, where you get these values and you have to actually plug them back into the function. You get x, plug it back in, and then find the area. It's not that much complicated. You just have to plug it in. Of course, you probably need a calculator for that, because these are very messy numbers. So I have some time, so I'll show you how to calculate the derivative. F of x is equal to, well, it was x over 4 squared, so it'll become x squared over 16 plus, and this has pi times this squared. So we could do, instead, we can do 40 minus x squared over, this is 4 pi squared, because it's squared, and then times pi cancels out one of the pi, so it becomes 4 pi. Both of these are just constant. So first we look at this and this. we can use the power rule for this, and we can use power and chain rule for this. First, let's look at this. We do 1/16 because that's the constant times 2, we're bringing that down, and then just times x. So it becomes 1/8 x, or x over 8. Second part is this. You do 1 over 4 pi, then you bring down the 2, and you do 40 minus x just to the power of 1. And don't forget, it's the chain rule. We have a negative x plus 40. The 40 just becomes 0 when you take the derivative. Negative x becomes negative 1. So you have to do minus 1, which means that this is a negative, not a positive. Minus 1 over 4 pi times 2 just becomes 1 over 2 pi. So it's 40 minus x over 2 pi. Of course, you can combine fractions, but that's simple algebra, which I believe I just wanted to show you the calculus of it. So voila, this is how you find the derivative. We have a little bit more time, just enough time to do one more example problem. And that's what I mentioned before. You have a cylinder, an open cylinder, let's say, and the surface area is 120 inches squared, and you want to maximize volume. How would you do it? In this case, surface area is 2 pi r times h. So that's the hard part. It's the lateral area. Basically, if you were to unfold the cylinder, you would get a rectangle, and that's basically the circumference times the height. So 2 pi rh plus pi r squared is the bottom area. We would do 2 pi r squared, but it's open, which means that the top is not closed. So you just ignore the top. This is geometry, so I'm not going too in depth on how I got the formula, but you said this equal to 120. You want to solve for h because if you solve for r, it'll be just way too complicated. You'll get a quadratic equation. So you get 120 minus pi r squared. You just subtract pi r squared from both sides and divide by 2 pi r. Now, what's the formula for volume? Well, volume is equal to pi r squared h. H we can replace in our function. Let's say it's x is the variable. R becomes x in this case, times 120 minus pi x squared over 2 pi x. And again, you should be able to calculate the derivative by hand. So you could do that if you want practice. I'm not going to because we're running out of time. And I already showed you how to calculate the previous one, which is, it wasn't that bad, but this is relatively easier because you can use algebra to simplify the variables and just get one quotient, I believe, and you can use quotient rule for that. You will get an f prime of x is equal to 60 minus 3 pi x squared over 2. This isn't too bad. You want to set this equal to 0. The previous example, though, this one, again, not too bad. You could do algebra, but you're going to probably get something in terms of pi. We got a decimal because we used a calculator. You would get something in terms of pi. So if we just solve this equation in terms of x, set it equal to 0, we're going to get some exact answers, but we want the decimals because decimals provide us more information. We're going to get x is equal to 3.568. That would be what your value of x is, which is the radius in this case. Let's say it wanted to know what the volume was, the maximum volume. So you just plug that back into this equation that you got, the one in terms of x, basically the function f of x. You plug in your value that you got, and if you were to calculate it out, you would get the maximum volume, and that would be 142.730 inches cubic. So that's how you'd solve this problem. We did have to write equations in terms of one variable in this, which is why I wanted to do this. The previous example was a bit more complicated because it's not as intuitive, but this one uses all the steps. So we drew a diagram, we wrote down the main equation, which is this. We wrote down the other equations. We solved for one variable and created this function. We used calculus to optimize it, and then we solved the actual question. All 6 steps in this problem. So a good job if you got the right answer on this problem. You could have paused while I was explaining and done it yourself. Again, you could find the derivative yourself to test out your calculus skills that you learned. And that's basically it for chapter 5. There's one more thing actually, and that's L'Hopital's rule. And it basically says if you have a limit as x approaches 0 of an indeterminate form, let's say x over sine x, you can take the derivative of the numerator, take the derivative of the denominator, and find the limit as x approaches 0 of that. So that's basically what L'Hopital's rule says. Derivative of x is 1, derivative of sine is cosine. So now you can plug in 0 into this, because cosine of x would not give you 0. Instead, cosine of 0 will give you 1. So you'll get 1 over 1, which is equal to 1. And if you were to graph it or use any other technique to find the limit of the original, you would get 1. So L'Hopital's is basically an easy way to say, if you have an indeterminate form, 0 over 0, it has to be 0 over 0, by the way, you can take the derivative of the numerator, take the derivative of the denominator, divide them, or take the limit as x approaches the value of that, and you'll get your answer. So that was the final topic of chapter 5. And we basically covered some derivative tools and applications. Tools included product rule, quotient rule, chain rule, and the trigonometric functions. Applications included extreme values, critical points, and the derivative test, and optimization, and now L'Hopital's rule. So that was chapter 5. We'll be moving on to chapter 6, which is some more derivatives and integrals. So I'll see you next time. Bye.